In digital signal processing, spatial anti-aliasing is the technique of minimizing the distortion artifacts known as aliasing when representing a high-resolution image at a lower resolution. Anti-aliasing is used in digital photography, computer graphics, digital audio, and many other applications. Anti-aliasing means removing signal components that have a higher frequency than is able to be properly resolved by the recording device. This removal is done before sampling at a lower resolution. When sampling is performed without removing this part of the signal, it causes undesirable artifacts such as the black and white noise near the top of Figure 1 or below. In signal acquisition and audio, anti-aliasing is often done using an analog anti-aliasing filter to remove the out-of-band component of the input signal prior to sampling with an analog to digital converter. In digital photography, optical anti-aliasing filters are made of birefringent materials, and smooth the signal in the spatial optical domain. The anti-aliasing filter essentially blurs the image slightly in order to reduce the resolution to or below that achievable by the digital sensor. Examples: in computer graphics, anti-aliasing improves the appearance of polygon edges, so they are not jagged, but are smoothed out on the screen. However, it incurs a performance cost for the graphics card and uses more video memory. The level of anti-aliasing determines how smooth polygon edges are. Figure 1 illustrates the visual distortion that occurs when anti-aliasing is not used. Near the top of the image, where the checkerboard is very small, the image is both difficult to recognize and not aesthetically appealing. In contrast, Figure 1b shows an anti-aliased version of the scene. The checkerboard near the top blends into gray, which is usually the desired effect when the resolution is insufficient to show the detail. Even near the bottom of the image, the edges appear much smoother in the anti-aliased image. Figure 1c shows another anti-aliasing algorithm, based on the sync filter, which is considered better than the algorithm used in 1b. Figure 2 shows magnified portions of Figure 1a and 1c for comparison. In Figure 1c, anti-aliasing has interpolated the brightness of the pixels at the boundaries to produce gray pixels since the space is occupied by both black and white tiles. These help make Figure 1c appear much smoother than Figure 1 at the original magnification. In Figure 3, anti-aliasing was used to blend the boundary pixels of a sample graphic. This reduced the aesthetically jarring effect of the sharp, step-like boundaries that appear in the aliased graphic at the left. Anti-aliasing is often applied in rendering text on a computer screen, to suggest smooth contours that better emulate the appearance of text produced by conventional ink and paper printing. Particularly with fonts displayed on typical LCD screens, it is common to use subpixel rendering techniques like ClearType. Subpixel rendering requires special color-balanced anti-aliasing filters to turn what would be severe color distortion into barely noticeable color fringes. Equivalent results can be had by making individual subpixels addressable as if they were full pixels, and supplying a hardware-based anti-aliasing filter as is done in the OLPCX01 laptop's display controller. Pixel geometry affects all of this, whether the anti-aliasing and subpixel addressing are done in software or hardware. Simplest approach to anti-aliasing. The most basic approach to anti-aliasing a pixel is determining what percentage of the pixel is occupied by a given region, in this case a pixel-sized square, possibly transposed over several pixels, and using that percentage as the color. A very basic plot of a single, white-on-black anti-aliased point using that method can be done as follows. Define function plot anti-aliased point, for round edge equals floor to seal do, for rounded e equals floor to seal do, %x equals 1, abs, %y equals 1, abs, % equals %x %y, draw pixel. This method is generally best suited for simple graphics, such as basic lines or curves, and applications that would otherwise have to convert absolute coordinates to pixel-constrained coordinates, such as 3D graphics. It is a fairly fast function, but it is relatively low quality, and gets slower as the complexity of the shape increases. For purposes requiring very high-quality graphics or very complex vector shapes, this will probably not be the best approach. Note: the draw pixel routine above cannot blindly set the color value to the % calculated. it must add the new value to the existing value at that location up to a maximum of 1. Otherwise, the brightness of each pixel will be equal to the darkest value calculated in time for that location, which produces a very bad result. For example, if one point sets a brightness level of 0.90 for a given pixel and another point calculated later barely touches that pixel and has a brightness of 0.05, the final value set for that pixel should be 0.95, not 0.05. Signal processing approach to anti-aliasing. In this approach, the ideal image is regarded as a signal. The image displayed on the screen is taken as samples, at each pixel position, of a filtered version of the signal. Ideally, one would understand how the human brain would process the original signal, and provide an on-screen image that will yield the most similar response by the brain. The most widely accepted analytic tool for such problems is the Fourier transform. This decomposes a signal into basis functions of different frequencies, known as frequency components, and gives us the amplitude of each frequency component in the signal. The waves are of the form where j and k are arbitrary non-negative integers. There are also frequency components involving the sine functions in one or both dimensions, but for the purpose of this discussion, the cosine will suffice. The numbers j and k together are the frequency of the component. J is the frequency in the x direction, and k is the frequency in the y direction. The goal of an anti-aliasing filter is to greatly reduce frequencies above a certain limit, known as the Nyquist frequency, so that the signal will be accurately represented by its samples, or nearly so, in accordance with the sampling theorem. There are many different choices of detailed algorithm, with different filter transfer functions. Current knowledge of human visual perception is not sufficient, in general, to say what approach will look best. Two-dimensional considerations. The previous discussion assumes that the rectangular mesh sampling is the dominant part of the problem. The filter usually considered optimal is not rotationally symmetrical, as shown in this first figure. This is because the data is sampled on a square lattice, not using a continuous image. This sampling pattern is the justification for doing signal processing along each axis, as it is traditionally done on one-dimensional data. Lanczos resampling is based on convolution of the data with a discrete representation of the sinc function. If the resolution is not limited by the rectangular sampling rate of either the source or target image, then one should ideally use rotationally symmetrical filter or interpolation functions, as though the data were a two-dimensional function of continuous x and y. The sinc function of the radius, in the second figure, has too long a tail to make a good filter. A more appropriate analog to the one-dimensional sinc is the two-dimensional Airy disk amplitude, the 2D Fourier transform of a circular region in 2D frequency space, as opposed to a square region. One might consider a Gaussian plus enough of its second derivative to flatten the top or sharpen it up, as shown. Functions based on the Gaussian function are natural choices, because convolution with a Gaussian gives another Gaussian whether applied to x and y or to the radius. Similarly to wavelets, another of its properties is that it is halfway between being localized in the configuration and in the spectral representation. As an interpolation function, a Gaussian alone seems too spread out to preserve the maximum possible detail, and thus the second derivative is added. As an example, when printing a photographic negative with plentiful processing capability and on a printer with a hexagonal pattern, there is no reason to use sinc function interpolation. Such interpolation would treat diagonal lines differently from horizontal and vertical lines, which is like a weak form of aliasing. Practical real-time anti-aliasing approximations, there are only a handful of primitives used at the lowest level in a real-time rendering engine. These include points, lines, and triangles. If one is to draw such a primitive in white against a black background, it is possible to design such a primitive to have fuzzy edges, achieving some sort of anti-aliasing. However, this approach has difficulty dealing with adjacent primitives. To approximate the uniform averaging algorithm, one may use an extra buffer for subpixel data. The initial approach used 16 extra bits per pixel, in a 4A4 grid. If one renders the primitives in a careful order, such as front to back, it is possible to create a reasonable image. Since this requires that the primitives be in some order, and hence interacts poorly with an application programming interface such as OpenGL, the latest methods simply have 2 or more full subpixels per pixel, including full color information for each subpixel. Some information may be shared between the subpixels. MIP mapping equals. There is also an approach specialized for texture mapping called MIP mapping, which works by creating lower resolution, pre-filtered versions of the texture map. When rendering the image, the appropriate resolution MIP map is chosen and hence the texture pixels are already filtered when they arrive on the screen. MIP mapping is generally combined with various forms of texture filtering in order to improve the final result. An example of an image with extreme pseudo-random aliasing, because fractals have unlimited detail and no noise other than arithmetic round-off error, they illustrate aliasing more clearly than do photographs or other measured data. The escape times, which are converted to colors at the exact centers of the pixels, go to infinity at the border of the set, so colors from centers near borders are unpredictable, due to aliasing. This example has edges in about half of its pixels, so it shows much aliasing. The first image is uploaded at its original sampling rate. The second image is calculated at 5 times the sampling rate and downsampled with anti-aliasing. Assuming that one would really like something like the average color over each pixel, this one is getting closer. It is clearly more orderly than the first. In order to properly compare these images, viewing them at full scale is necessary. It happens that, in this case, there is additional information that can be used. By recalculating with the distance estimator algorithm, points were identified that are very close to the edge of the set, so that unusually fine detail is aliased in from the rapidly changing escape times near the edge of the set. The colors derived from these calculated points have been identified as unusually unrepresentative of their pixels. The set changes more rapidly there, so a single point sample is less representative of the whole pixel. Those points were replaced, in the third image, by interpolating the points around them. This reduces the noisiness of the image but has the side effect of brightening the colors. So this image is not exactly the same that would be obtained with an even larger set of calculated points. To show what was discarded, the rejected points, blended into a gray background, are shown in the fourth image. Finally, budding turbines is so regular that systematic aliasing can clearly be seen near the main turbine axis, when it is downsized by taking the nearest pixel. The aliasing in the first image appears random because it comes from all levels of detail, below the pixel size. When the lower level aliasing is suppressed, to make the third image and then that is downsampled once more, without anti-aliasing, to make the fifth image, the order on the scale of the third image appears as systematic aliasing in the fifth image. Pure downsampling of an image has the following effect. Supersampling/full scene anti-aliasing. Supersampling anti-aliasing, also called full scene anti-aliasing, is used to avoid aliasing on full-screen images. SSAA was the first type of anti-aliasing available with early video cards. But due to its tremendous computational cost and the advent of multi-sample anti-aliasing support on GPUs, it is no longer widely used in real-time applications. MSAA provides somewhat lower graphic quality, but also tremendous savings in computational power. The resulting image of SSAA may seem softer, and should also appear more realistic. However, while useful for photo-like images, a simple anti-aliasing approach may actually worsen the appearance of some types of line art or diagrams, especially where most lines are horizontal or vertical. In these cases, a prior grid fitting step may be useful. In general, supersampling is a technique of collecting data points at a greater resolution than the final data resolution. These data points are then combined to the desired resolution, often just by a simple average. The combined data points have less visible aliasing artifacts. Full scene anti-aliasing by supersampling usually means that each full frame is rendered at double or quadruple the display resolution, and then downsampled to match the display resolution. Thus, a 2x FSAA would render 4 supersampled pixels for each single pixel of each frame. rendering at larger resolutions will produce better results. However, more processor power is needed, which can degrade performance and frame rate. Sometimes FSAA is implemented in hardware in such a way that a graphical application is unaware the images are being supersampled and then downsampled before being displayed. Object-based anti-aliasing: a graphics rendering system creates an image based on objects constructed of polygonal primitives. The aliasing effects in the image can be reduced by applying an anti-aliasing scheme only to the areas of the image representing silhouette edges of the objects. The silhouette edges are anti-aliased by creating anti-aliasing primitives which vary in opacity. These anti-aliasing primitives are joined to the silhouetted edges, and create a region in the image where the objects appear to blend into the background. The method has some important advantages over classical methods based on the accumulation buffer since it generates full scene anti-aliasing in only 2 passes and does not require the use of additional memory required by the accumulation buffer. Object-based anti-aliasing was first developed at Silicon Graphics for their Indie workstation. Anti-aliasing and gamma compression: digital images are usually stored in a gamma-compressed format, but most optical anti-aliasing filters are linear. So to downsample an image in a way that would match optical blurring, one should first convert it to a linear format, then apply the anti-aliasing filter, and finally convert it back to a gamma-compressed format. Using linear arithmetic on a gamma-compressed image results in values which are slightly different from the ideal filter. This error is larger when dealing with high contrast areas, causing high contrast areas to become dimmer, bright details become visually thinner, and dark details become thicker, relative to the optically anti-aliased image. Because the conversion to and from a linear format greatly slows down the process, and because the differences are usually subtle, almost all image editing software, including Final Cut Pro, Adobe Photoshop and GIMP, process images in the gamma-compressed domain. History: important early works in the history of anti-aliasing include Freeman, H. Computer Processing of Line Drawing Images. ACM Computing Survey 6, 57 Euro 97 doi, 10.1145/356625.356627. Crow, Franklin C. The Aliasing Problem and Computer-Generated Shaded Images. Communications of the ACM 20, 799 Euro 805 doi, 10.1145/359,863.359869. Katmull, Edwin. A Hidden Surface Algorithm with Anti-aliasing. Proceedings of the 5th Annual Conference on Computer Graphics and Interactive Techniques, pages 6 Euro 11. See also, alpha to coverage, anisotropic filtering, color theory, font rasterization, measure theory, reconstruction filter, saffron type system, sampling, subpixel rendering, temporal anti-aliasing, texture filtering, Xiaolin Wu's line algorithm. References. External links: Anti-aliasing and transparency tutorial, explains interaction between anti-aliasing and transparency, especially when dealing with web graphics, interpolation and gamma correction in most real-world systems. Gamma correction is required to linearize the response curve of the sensor and display systems. If this is not taken into account, the resultant nonlinear distortion will defeat the purpose of anti-aliasing calculations based on the assumption of a linear system response. The future of anti-aliasing, a comparison of the different algorithms MSAA, MLA, DLAA and FXAA, French, Le Roller du filtre anti-aliasing dans l'APN.